The filter circuits are used to select one kind of frequency signals and reject the other kind of frequency signals. Whatever be the voltage level, that is not a concern. The frequency of the signal is the concern over here. The cutoff frequency is the frequency above or below which we are going to choose a signal. So based on the type of filter that we are going to design, the cutoff frequency varies. Let's discuss all of that in this video. Let's get started. There are two kinds of filter circuits. One is the passive filter circuit, which uses passive components, and the next is the active filter, which uses components like OPAMP for more signal conditioning, voltage amplification and all. So the active filters use OPAMP. We are going to talk about this only at the end of the video, where we are going to see how these passive filters are applied over to the active filter. Okay, so first we will understand how a passive filter works. There are four types here. One is the low pass filter, high pass filter, band pass filter and band reject filter. Okay, so this low pass filter is very simple. The passive filter uses only components like R, L and C without any power element involved in the circuit for signal conditioning. So in the passive filter of low pass filter, we have a series resistance R1 and this is the capacitance C1. Okay, so we are going to apply the signal input to this series circuit and choose the output that is across this capacitor. In a series circuit, the voltage divides, right? So the voltage across this capacitor will be the output for the low pass filter. How is it possible? Why should we not take the voltage across the resistance? We are going to understand that in detail. Okay. So what is the output voltage? This is equal to the input voltage times the capacitive reactance divided by resistance plus the reactance. This is just the voltage division rule. Okay, so for those of you who do not know this rule, you can check the link that is appearing above and watch the video on voltage division rule and jump back here. Okay, so in short, we are going to find out the voltage division across this capacitor, which is the output voltage. Okay, and this component will also be the gain, the filter's gain. Okay, so let's see what this is. V out will be V in multiplied by 1 by j omega C1 divided by R1 plus 1 divided by j omega C1. Okay, I am just expanding the term XC1. XC1 is equal to 1 by j omega C1, right? So this is equal to V in multiplied by 1 divided by R1 C1 j omega plus 1. I am just taking the LCM and cancelling off the common terms. Okay, so what is V out by V in? The filter's gain, right? Output voltage divided by the input voltage, which is the gain. This is 1 divided by 1 plus j omega R1 into C1. Let's split out the real and imaginary terms out of it, because that will help us to determine what is the cutoff frequency of this filter. Why should we do that? Let me draw you the response. Okay. What is the objective of the low pass filter? The low pass filter will filter the low frequency components and it will actually start to reject the high frequency components. So the cutoff frequency is this frequency where the gain is the actual gain divided by root 2. This is defined as the cutoff frequency, or in short, this will be 70.7% times the total gain. Okay, so beyond this gain, this will be in the reject band, and this band of frequencies is the pass band. Okay, we know that at cutoff frequency, the gain is the total gain, that is the maximum gain divided by root 2. We are going to apply this concept into this equation. At cutoff frequency, the frequency will be omega c, and the gain will be the total gain times the root 2. Okay, it is so 1 by root 2 will be 1 plus j omega r1 into c1. So how to find out the magnitude? We have to take the conjugate and multiply on numerator and denominator, right? So this will be 1 minus j omega r1 into c1 divided by 1 plus omega c, sorry, because this is at cutoff frequency. So 1 plus omega c square r1 square c1 square. Okay, so what is the magnitude of it? The magnitude will be 1 divided by 1 plus omega c square r1 square c1 square. We are interested in it because we are talking only about the gain's magnitude, which is 1 by root 2 times the original magnitude. So 1 divided by root 2 will be, the square root of this. 1 divided by the square root of 1 plus omega c square r1 square c1 square. So this implies that 2 is equal to 1 plus omega c square r1 square c1 square. So I am taking this 1 to that side. So 2 minus 1 is 1. 1 is equal to omega c square r1 square c1 square. So what is omega c? 1 divided by r1 into c1. This is the cutoff frequency of a low pass filter. Okay, so this low pass filter filters the circuit voltage gain up to a frequency called as a cutoff frequency, and beyond that it will be rejecting all those signals. Okay, so this is a low pass filter. Next we are going to talk about high pass filter. If Vin is the input voltage that is applied across the RC circuit, for a high pass filter we are choosing the voltage across this resistance instead of this capacitance. If we choose to select the voltage across this capacitance, this is called as the low pass filter, and if we find out the voltage across this resistance, then this is called as a high pass filter. So what happens in a high pass filter? In the same way, what is V out by V in? V out by V in will be the voltage component across this resistance, which is R1 divided by XC1 plus R1. Okay, what is this? R1 divided by 1 by j omega C1 plus R1. So if we simplify this, we will be getting j omega R1 into C1 divided by 1 plus j omega R1 into C. By the definition of high pass filter, so what is omega h? Omega h is the cutoff frequency of high pass filter, beyond which the gain is stable. This gain, let us say this is A, and this will be A divided by root 2. So when the frequency is greater than A by root 2, that signal will be appearing across the output. Okay. So using this definition, we will apply into this equation. It is just the same. Okay. So what is the magnitude of the gain? The magnitude of the gain will be 1 divided by root 2 times A, which is equal to, we have to take the conjugate of the denominator and simplify. Okay. So if we take the conjugate, it will be, and just park this aside. Okay. So this is equal to plus omega square r1 square c1 square divided by 1 plus omega square r1 square c1 square. So what happens at cutoff frequency? At cutoff frequency, the magnitude of this will be 1 by root 2, which is equal to 1 by root 2 times the original gain. Okay, so this is equal to omega h square r1 square c1 square 1 by 2 times A, I am sorry, divided by square root of 1 plus omega h square r1 square c1 square. So again, if you simplify, you will be getting the value of omega h as 1 divided by r1 into c1. Okay, this is just a basic simplification which you all can do. Okay, so in short, in a series RC circuit, if we are choosing the output across the capacitor, this is a low pass filter, and if we are choosing the output across a resistor, this is called as a high pass filter. Let's combine both of them and form a band pass filter. Band pass filter is a combination of high pass filter and a low pass filter. Because if you just observe the curve, we are going to select above a particular frequency but below a particular frequency. That is called as a band pass. Okay, I'll explain you in a minute. This is the frequency and this is the gain. So in a band pass filter, we will be filtering the signal above a particular frequency but below a particular frequency. So in between these two frequencies, which is called as omega C1, which is the higher cutoff frequency, and omega C2, which is the lower cutoff frequency. So there are two parts in it. One is the high pass filter, where we are choosing the output voltage across this resistance, and we are connecting that, we are cascading that with another low pass filter. Okay, in a low pass filter, the input voltage is applied across a RC circuit, and we are taking the output voltage across this capacitor, right? So to get this part of the curve, which is like a low pass filter, we are choosing this part, which is a low pass filter, and this is a high pass filter. Okay, so the combination of both these is your band pass filter. So what is the value of omega C1? 1 divided by R1 into C1. So what is omega C2? It is 1 divided by R2 into C2. So this is a very simple concept, right? Using passive components, we can design the filter circuit. Similarly, for a band reject filter, how should you design this circuit? You should have a high pass filter cascaded with a low pass filter. Okay, so I want you all to take your notebook, draw the waveform of a band reject filter, because this is going to reject one band of frequencies. If the same thing, okay, if it is up to a particular frequency, it will pass. Above that, above omega C2, it will pass. This is the reject band. Okay, this will also be passed. This will also be passed. So how to design this circuit using same R and C elements? You can use the concept of band pass filter and cascade low pass filter first and then the high pass filter. Okay, so I want you all to draw the circuit by your own self just by knowing this concept and check if your answer is right. Okay, now we will move to the active filters. Active filters are designed using OPAMP because we want some more out of the passive filter, because we want to we just don't want to select a particular frequency band, we also want to amplify that frequency band. That is the reason why we go for active filters. So in an active low pass filter, we will have a low pass filter followed by an OPAMP. We will have a low pass filter R1 in series with C1, and this will be applied to the OPAMP's non-inverting terminal. We will be applying a voltage input over here. This is RF, this is RG. So the voltage at the non-inverting terminal is the voltage across this capacitor V1. Okay. So we are applying V1, which is the filtered output, to the OPAMP, and we are getting the output V out, which is equal to 1 plus RF by RG times V1. What is V1? The filtered output. This is the filtered output. Okay, this V1 is the voltage across this capacitor. Similarly, for a high pass filter, how will you design? It is just the same. We will be swapping both these components. For a high pass filter, okay, for a high pass filter, we will connect the C1 here and connect the R1 like this. Okay, so now this will be the output V1, which is across this R1. Okay, so this is a high pass filter. Similarly, for a band pass filter, you can cascade a high pass filter along with a low pass filter like this. This is going to be a high pass filter, so I am just denoting the resistances as RGH and RFH. And we are going to apply the V in here. This will be grounded. So now we have designed a high pass filter, and we are going to connect this to the non-inverting terminal of a low pass filter. The inverting terminal, what will be connect? You all know. It's going to be one series resistance RGL, because this is a low pass filter. I am just denoting it by a subscript L, and this is RFL. Okay, so to this we will have a resistance which is called R2, and this capacitance is called as C2, right? Sounds simple? We are just connecting one high pass filter to a low pass filter, because in a band pass filter what happens? We will have two bands. One is the pass band and one is the stop band. So this high pass filter will pass the signals above a certain frequency, right? This is a high pass filter. And what will happen to the low pass filter? This will reject the frequencies which are higher than 1 frequency, because it allows only lower frequencies from this output. This is omega C1, omega C2. What is omega C1? 1 divided by R1 multiplied by C1. So what is omega 2? Omega C2. Omega C2 is R1 by R2 into C2, right? This is the pass band. These signals will be rejected and also these signals will be rejected, right? This is the band pass filter. I want you all to apply this concept to band reject filter, which will be rejecting one band of frequency, and below this band also it will allow, above that band also it will allow. In this band of frequency, this signal will be rejected. This is band pass filter. I want you all to draw the circuit of a band pass filter and send it to learningtoengineer@gmail.com, because it's easier to find it in books or in the internet. You will just see the circuits and kind of memorize. I want you all to apply this concept. Just one simple thing, that if you select the voltage which is across a capacitor, it becomes a low pass filter. If you select that across the series resistance, it becomes a high pass filter. It is just greater than and less than symbol. Okay, so I want you all to apply this single concept and design the band rejects filter by your own self. Thanks for watching. And also, one of you have asked this in the comments, and that is why I had to add this. I thought that this is a very simple topic and I kind of omitted this, and as I gone through your comments, I felt you need this topic, and thus I kind of changed my schedule and I added this filter circuits now. In my next video, I'll be talking about diodes. Actually, I know that diodes is the LKG of semiconductor devices. You should be learning diodes first, and then BJTs, and then JFETs, MOSFET, and then OPAMP. That is how the syllabus is designed. But now I am doing a bottom-up approach. I am following only the OPAMPs first, which includes almost all the semiconductor devices, and then I had come to the V2I converters, then the filters, then the diode, then I will be going to BJTs, and I'm just following in the reverse order, so that you will be applying this from what you have learned already. First, I would have taught you the applications, which is the applications of OPAMP. I would have talked about signal generators, Astable multivibrator and all. So from applications, I come to diodes. Okay, so in my next video, you will be learning about diodes. Thanks for watching. If you have any thoughts about this channel, this playlist, or anything in mind, you can just type that down in the comment section, or you can email them to learningtoengineer@gmail.com. Thank you.